improving efficiencies in MRO facilities with GNSS repeating systems. I am going to hand you over to our presenter, Chris Bolton. Welcome, Chris.
Thanks, Amanda. So good morning, everyone. So yeah, as Amanda said, we'll be talking about improving efficiencies in MRO facilities, specifically using GNSS repeater systems. So what we'll be discussing today, just briefly about the company, Chronos Technology, a brief history of GPS and how it works, ADS-B, which is the avionics industry specification for the latest uses of GPS and GNSS, and the challenges that ADS-B integration presents for MRO facilities, and how GPS repeaters can help this. So, Chronos Technology was founded in 1986, so we have over 30 years experience in designing, implementing and supporting synchronization infrastructures and Tier 1 networks. Since about 1999, Chronos has also installed GPS distribution and repeating systems, firstly in large military maintenance hangars before moving on to non-military industries to provide GPS testing in production houses, rapid response, both military fast jets and civilian emergency services. A little about myself. I started in Chronos in 2006, initially helping in the build and test lab, before moving on to install GPS antennas for the telecoms Tier 1 companies, as discussed, on rooftops all over the world. I've worked on many UK military sites installing these GPS repeater systems up in the rafters of the large maintenance hangars. Altogether, I've completed many GPS installations across 14 countries and 3 continents, with each environment offering a different challenge. In 2014, I moved into the GNSS sales support engineer role, assisting day-to-day GPS distribution inquiries, antennas, splitters and filters, etc., while also helping to design these large, complex GPS distribution systems. So you can see there the global reach we have and the many varied places we've installed. So a brief history about GPS. GPS is the USA's global navigation satellite system, but there are others. There's rival constellations in Russia called GLONASS, in China called BeiDou, and the European Union have one called Galileo. It was initially commissioned by the US Department of Defense, so it's a military system initially, but is now operated by the US Air Force Space Command. So as discussed, it was initially for military users only, but they opened this up to all civilian aircraft or civilian users in 1983, but at a reduced accuracy. Initially, you could only get around 50 meters accuracy, but after an event in the year 2000, they switched this down to 5 meters. So you can see there the graph on the left, which is courtesy of the gps.gov website. So selective availability was switched off overnight, and you can see the accuracy jumping from 50 meters down to 5 meters, meaning that anybody can use this signal for their car sat-nav, and most importantly for us here, for aircraft navigation. So how does GPS work? So GPS is a constellation of 33 satellites, currently 31 in orbit, to get complete global coverage. They're approximately 12,500 miles away, which means it's an extremely weak signal by the time it reaches the Earth. So we'll discuss that later. GPS satellites transmit multiple codes. So L1 is the standard civilian signal we all receive using our car sat-navs or on our mobile smartphones. But there's also L2 signals and L5 safety of life signals, giving you higher accuracy using these encrypted messages. All GPS devices are receive only. They just use the difference in the time of arrival of the transmitted message from the satellite. Once you've received that message on the Earth, you can work out the approximate range, and using approximate ranges of multiple satellites, you can triangulate a position in 3 dimensions, as well as the accurate time, which is what the telecoms industry mostly use it for. So on to ADS-B. This is the reason that a lot of MRO facilities are having to use GPS repeaters now. So ADS-B is the Automatic Dependent Surveillance Broadcast. What this does is a replacement or a complementary service to traditional radar systems. So there's a lot of areas, the large oceans, for example, or large areas in China, Russia, US, Canada, that aren't covered by radar systems. So once the plane has gone away from the range of a large city, the air traffic control can no longer accurately track them. What ADS-B does is use the GPS or GNSS receiver on board the aircraft already and transmits that location over a dedicated VHF link to the air traffic control. They then use this location data to populate a map and update a real-time map of where all the aircraft are based on their GNSS. So aircraft have always used GPS or GNSS for a long time as navigation aid, but are now required to have GNSS to have ADS-B out to travel through certain airspaces. The US now require this. The EU is bringing in this as an implementation. So what are the challenges for aircraft maintenance? So on the runway, on the tarmac, or in the air, you have no issues. The GPS signal from the satellites can reach the plane with absolutely no obstructions. But by the time you put the aircraft into a hangar, by the time the signal reaches us here on Earth, it's heavily attenuated by the ionosphere, an extremely weak signal. It's about equivalent to a car headlight being seen from New York to London. As such, they will not travel through most building materials, brick or metal cladding especially. So what we can propose is using a GPS repeater. As you can see here, the GPS repeater system consists of three main components: the antenna, the amplifier, and the active antenna, the amplifier and the passive antenna. We also always suggest using a lightning arrestor for any lightning strikes. This simple setup will bring around 30 meters of signal indoors, though we do use splitters and further repeaters for larger hangars, splitting the same signal across the whole hangar. So how they work is receiving the GPS signal at the active antenna location, and then essentially transmitting that same data through the repeater. So no matter where you are inside the building, no matter how many repeaters there are inside the building, your receiver will always think that you're at the active antenna location up on the rooftop. This obviously does have some advantages and disadvantages. So the active antenna location, being a known static location, will always give you a good benchmark to test your equipment against, but you won't actually track where you are within a large hangar, for example. So what are the main benefits of this? To tow an aircraft outside of the hangar can be a time-consuming task, distracting several workers to operate the tow machine, walking the wing to watch for obstructions, etc., while also disrupting other workers who may need to move their operations to allow for the aircraft to move past. Once the GPS has been tested, this process will need to be reversed to bring it back in. To avoid this disruption, quite often the GPS system is the last thing tested during its maintenance. With tight time schedules, the extra time wheeling the aircraft out, if it can be in that state, to test one feature before wheeling it back in can be so detrimental. It's instead hoped that everything will work as it leaves for the final time. And if a fault is found then, once out on the tarmac, major delays can arise. Beyond these savings in engineer time, another cost in testing GPS outdoors brings is the loss of internal environment. So in hot countries, as soon as you open those large hangar doors, the air conditioning is instantly lost, and in colder countries, the heating will escape through those large doors. With a repeater in place, the GPS system can simply be tested by one engineer climbing into the cockpit, switching on the avionics and seeing that the signal is being received as expected, saving a vast amount of time and money. It's not just the aircraft industry that can benefit from this. So we've installed GPS repeater systems for a whole host of other industries. R&D facilities, so bringing distribution across an entire building. Quite often there we have a lot of splitters involved, a heavy amount of link budgets that all need to be calculated. End-of-line production testing is very similar to the R&D situation. In both of those, they can either be repeated signals over the air, or they could be hard points for directly connections to the receiver itself, bypassing an antenna. Onto emergency services and military fast response. So in both of these use cases, they want to have an up-to-date signal with the current data and information ready to go as soon as they jump into that vehicle, allowing them to track their vehicles and respond a lot faster. Cautions. So there are several things to look out for when installing a GPS repeater system. So the poor antenna installation can lead to errors for the receivers inside. So the diagram I showed earlier, the antenna is above the roofline, but in some of these pictures here, you can see that they're actually much, much lower. And these are antennas we've encountered out on our installations, often replacing these antennas because they perform so poorly. So you get shadow. This is essentially where the antenna can't see the full view of the sky. So if you can't see half the sky, you only get half the satellites, and reducing your location accuracy. However, multipath is a larger issue there. So these signals can bounce off of RF reflective surfaces very easily, especially metal and brick. What this does is extend the range, or extend the time of arrival of that signal to reach your antenna. And in the calculation, this extends the range and will lead to errors in your triangulation. So these antennas we can see here, the top right and the bottom right especially, they're extremely attenuated by the buildings in the way, and the signals they can see will be extended by multipath and thus lead to huge errors. Poor coaxial connections. So a poor connection can often lead to intermittent issues, which are far more frustrating for users. And other strong RF power sources. So again, we can see on the far right there, those antennas are near other antennas that may be transmitting on a similar frequency. We've also seen large UPS batteries or large power generators, or even air conditioning units causing spikes in relatively close proximity to the antenna's frequency. So that's the active antenna installation causing issues, but the repeater as well could lead to issues if not properly installed. The repeater signal being seen outside mixing with real signals can lead to very confused receivers, as their location will jump from their actual location on the road or the tarmac to the repeated location from the rooftop antenna location. To combat this, we always try to aim to have the repeater facing inwards into the building, not out onto the tarmac. We have seen installations in the past that have caused issues in that regard. It's always something that should be checked properly before utilizing. Some countries require a license to operate GNSS repeaters. So here in the UK, we have Ofcom. It's a very simple process to apply for this license, but others are a bit more strict. So it's always something to be aware of, whatever your local regulatory body requests. So in conclusion, testing of GPS systems is becoming more and more important to aircraft maintenance, especially with ADS-B becoming a requirement. GPS repeaters allow this testing to be performed optimally, cutting down engineering time, cost, and complexity. Since 1999, Chronos technology has been helping to design, supply, install, commission, and support these GPS repeater installations across the world. We're always happy to help. So, any questions at all?
Thank you, Chris. That was very interesting. I'm going to check our questions now. I think we have a question from Dave who asks prices. How much is a typical GPS repeater setup?
So we found there's not often a typical repeater setup. There's a lot of differences in antenna locations, so requiring different mounting methods. Different cable lengths require different cable types to be used due to the losses, and what GPS signals are actually required indoors. a standard GPS L1 civilian repeater will be a lot less expensive than a full GNSS requirement. In some settings, we can complete an installation in a single day, whereas larger industrial sites or multiple smaller sites, so the fire stations, for example, around a local authority, could take weeks of engineering time, driving up the complexity. But there's not really one standard build that we often find. So we're always happy to help from the initial planning stage of any GNSS repeater requirement. So just please get in touch and we can discuss from there what your requirements are.
Thank you. Hopefully that's answered your question, Dave. John asks, you mentioned repeaters may require a license. Are you able to answer that question?
Yeah, so just to expand on that really. So different countries have different regulatory bodies and they all have different rules, and some are stricter than others. So here in the UK we have Ofcom, and it's a very quick and easy process to apply for that required license. All the application form really asks is where the repeater is, who is responsible for it, and what signals are being repeated. And there's a small one-off fee for this, for a lifetime license. It's just a register to make sure that they know where all the repeaters are, and if anyone complains about interference in that area, they'll know who to ask first. But it's a very low-key and easy form. So with the Ofcom license, in some projects, we've applied for this license on behalf of the customer using the information from our site surveys and commissioning to complete our turnkey solution. Other customers have elected to apply for this themselves otherwise. Yeah.
Thank you very much. I hope, John, that's answered your question. That now is the end of our Improving Efficiency with GNSS repeating webinar. I do hope that you've found the talk that Chris gave interesting and informative. We welcome you to the next one. Goodbye.